0. Okay, so let's see if we can continue to streamline our in-class time. So we'll do the background or a substantial chunk of it because there's a lot in the pre-lab, which is really the point of the pre-lab. So, and I forgot. Let's see, did I have this set up right? Yep. So, we have some objectives here. And this is really kind of like what we're going to be doing in a way. This is the end result, right? We're going to verify Faraday's law of induction, it's called. When magnetic fields do things to other things, we say they induce, and that's where the word induction comes from. And we're going to use some stationary coils with varying distances, and then we're going to have a spinning coil, which we can vary the spinning speed. Okay. So, and I'll bring this into the classroom too, both lecture and lab. So people observed that, and I don't know, Faraday, well, it's Faraday's law, right? That, that we could have a current in a wire, and the current in the wire can make a magnetic field, and we can turn a compass. Well, it turns out I can just have a plain old wire, and I can put a magnet near it, and it has to be moving though. And we can observe a current, and the best way to do it is to make a coil. And so as we approach this thing, we'd see the needle move. There'd be some current going round and round. And then once it's in there, if we pull it back out again, we would see the current swing the other way. So maybe to the right is down, and to the left is pulling it back up. And we call it an induced current. And in fact, this is basically what I always think about it, but strictly speaking, it's an induced voltage. Because it turns out that even if I were to break this wire so there's no longer a complete circuit, there would still be a voltage to be measured. And so this is a galvanometer, for example. So it has a very low resistance, but it produces, it allows a complete circuit because, remember, current through, voltage across. I could put a voltmeter here, and even if, so the voltmeter, remember, doesn't, because the resistance of the voltmeter is so high, we don't think of it as a complete current path if the voltmeter was connected and no ammeter. And we'd still see an EMF. Okay, so it's an induced EMF. And I try hard not to screw it up, but I'm just so used to calling it a current because it is kind of useless to settle this up and not connect it to anything. Now what we can also do is we can put one coil inside of another, or even one coil could just be next to each other. And there's if you have a current, you would have a B, and of course the B field has to come back, but one coil will produce, so this inner coil, for example, represents the permanent magnet. But in this case, well, you could actually move it up and down, yes, but if you simply change the current in the coil by turning it off and on, you would see a current here. So certainly the powered coil with a constant current, you can move it up and down like a bar magnet. But you can hold it stationary and simply change the current in the powered coil, and you'll see a reaction in the passive coil. Now, and as you probably can imagine, the B field within the passive coil is changing. Because in this case, don't forget, the magnetic field spreads out, and as we get closer, more and more of these lines coming out of here will now fit inside the coil, the passive coil. All right, so one nice thing at least, we've gotten this far in lecture, so we can define a magnetic flux, the equivalent of electric flux, or an analog of electric flux, I suppose. And we still use this A vector that, remember, is sort of a contrived vector. And it's perpendicular, and we generally put it in the middle of the area. And so, and we use the dot product with cosine, which I screwed up in lecture at first. And from now on, the way we're going to do things, well, let's think about this. No, sometimes theta won't be 0, but so the max, all we want to say right now is that the maximum flux happens when the B field and the A vector are lined up. Okay, and so Faraday's law, and this is, this is more not a derivative here. At the moment, we're just simply saying that if there's a change in flux in time, that there's going to be an induced EMF in the object in the object that has the changing flux. Now, of course, we've defined it as this angle, but it turns out there's 3 different ways it could change, because notice there's 3 terms in our flux equation. The area can change, the magnetic field can change, and the angle can change. And also, this minus sign is there. We're going to go into it some more. But you can come up with it from a thing called Lenz's law, but the simple way to understand it is that if it didn't, it would violate thermodynamics, because we could just create energy out of nothing. Because what happens is the induced EMF rotates in a way that it produces a magnetic field in the opposite direction. If it produced it in the same direction, you can imagine we'd have a runaway EMF. We could all get rich and go home and never work again in our lives, because we could produce electricity for nothing. But of course, that doesn't happen. So if we now define Faraday's law as a derivative, and we say we're going to allow all 3 of them to have a time dependence. Now, one thing, let's be careful here. Let's notice a change. It said theta here. And in this case, theta is sort of, you set it at something, but we want to introduce time dependence. And so essentially what we're saying is this T B is a function of t, And now we're saying theta is a function of t. Because cosine is cosine, and there's no such thing as time dependence on cosine. But what we're doing is that we're saying that the interior here is got some time dependence. And so we're going to use our old friend. Remember, the theta is in radians and radians is well, first of all, we're using theta, right? We always use radians. And then this is radians per second because we can think of this as something spinning, well, because that's exactly what we're going to see. So we use our chain rule. We take the time derivative of the first times the other two, then the time derivative of the second times the other two, and then the time derivative of the third times the other two. Now, let's see what we've got here. Well, of course, this becomes negative cosine, negative sine of omega t, derivative of cos. And first of all, derivative, don't forget, is the cos of anything. If you say dt, this equals minus sine of whatever's in there multiplied by the time derivative of what's inside. Oh, I guess I'm going over that in the next slide. So we would take the time derivative of this. So let's wait on that for a moment. Apologize. And there it is. And so since it's negative, we took the negative of that expression earlier. And remember, the derivative of cosine is minus sine. And then we took the derivative of the inside. And so notice that the induced EMF is omega dependent. So the voltage coming out, the EMF, if we plotted time and either EMF or the flux, it's not shown here, but if we changed omega, this voltage peak to peak, for example, would change. Excuse me. So if you spin it spin faster, the flux changes faster, and that means the amount of the EMF it changes faster. Wait a minute. And so that changes faster, but it also means that the magnitude of the EMF gets larger. It changes fast. So EMF changes faster, but the magnitude changes as well. So if we went faster, we would show these sine waves would scrunch together, but they would get bigger. Okay, so let's take a look at this. And we just added an n here because this is the number of turns in our coil. Remember the rotating coil. This is for a single loop. And let's see what we got here. Right. So, defy dt. But what we can do is remember that if you have you can have a general statement of sine omega t, and this is the amplitude So we're defining the amplitude as the so-called epsilon 0. And basically, we're just simply saying it's everything in front of the sine function. That's all. So what that means is that, and let's make this a little bigger. Oh, and by the way, you're welcome. I'm going to post this as a PowerPoint slide in slides, and you can copy paste any diagrams, but not equations. So of course, we always measure peak to peak with an oscilloscope, but the voltage we measure here, this is our EMF sub 0. Excuse me. So also remember that omega equals 2 pi f. This should all be familiar from Physics 2100. So then epsilon EMF equals B capital N A, which don't forget it's the area of the coil, and in this case the spinning coil, 2 pi f. And you see that we can solve it for like this. And A. Okay. So what we can do is that we can actually, so we are going to, right. Well, yeah, I'm going to show you the apparatus now. So what we can do to determine this is that we can control omega, and then we would measure the amplitude of the output. So this means then that we can make a graph of omega or frequency, I suppose, right? Because that's easier. And for the moment, we'll put that there. But let's see what happens if we rearrange this equation. So in fact, we are going to use this equation for analysis. This is just our background. Excuse me. So since, this is the thing we measure, and we'll say that, so B N A 2 pi f, and we can define this as the slope. So if we take a variety of points, different frequencies, and measure the resulting EMF, then the slope is equal to B N A 2 pi. So since all those other quantities are constants that we can plug in, we can find the slope, and we can solve for B, and this is going to be the slope divided by NA 2 pi, and we also know how to get the plus minus slope and plus minus B, but that will be in an analysis video. For now, we just want to talk about the data we have to collect. Okay, so now I guess I'm sort of skipping to procedure here. Maybe I should talk about, let's stick with background, and then I'll loop back to procedure. Okay, so the other part we're going to do, and so this is part B, that's part C, and we may not do them in this order. And this is part A. Of course, we use A again, huh? But there's only so many letters. Okay, so let's take a look here. We know, we've seen it in class, and we've used it in the magnetism lab, and we set Z equal to 0. But now we're going to have a coil and another coil. So first of all, so then Z, well, we can start with Z equals 0, I believe. I don't remember now off the top of my head. Yeah, we could, because we're going to define this variable in a little while. But anyways, we're going to have a coil, and we're going to put a magnetic field in it, and we're going to actually put, this is the basic equation, but we're going to put a time varying B field here, and then we're going to measure the induced EMF here, and then we're going to then be able to get the B in the surge coil. That's the overall thing we're doing. Okay, so this is the equation for if there is some current in this coil. We can plug in all these numbers, and we can get the B field as a function of along the axis here, Z. So now what we'll do is we'll make I time dependent, and this is how we can make B time dependent. And so it's really simple. We're going to slap a cosine omega t onto it. That's it. And this I becomes an I sub 0. And in this point, it's I amplitude, and which is, of course, half of I peak to peak. So we have to figure out how we're going to measure that, but we'll get there. So we can plug, we could just say that this B0, so now let's see. So B0 again is that, and that's all we care about. All we did, as I said, is we throw in the 0 because, again, we measure peak to peaks. And so we can drop the cosine term out of there because we just want the amplitudes. And we can rearrange this equation like this. And just to have a way of simplifying everything. And we define this variable of Z over A. And you notice then that the well, not the complete denominator, but if we substitute that into here, we get this. So this here is an equation that we're going to use at some point. And now let's think about the search coil. So the search coil is going to be the EMF in there is going to be the changing magnetic field in that coil times the number of coils it has, and the capital A area. This is, remember, the radius, so it's somewhat different. Remember, area is radius squared, right? So there's a relationship there. So let's think about this. Excuse me. So it turns out, though, the way we're doing this is no longer a constant, right? It's this the field of this coil and we're moving the search coil. So this is not a constant. You have to be careful there. And this V0, this is at the distance Z. So B0 is always at Z. Okay, so notice then, well, let's see what we got here. We just need the amplitude, and so we see that we just had to pull out this omega, and we take the time derivative, and we just going to define that once again, as we did before. So we take the time derivative here, we're going to get B sub 0 NSA with an omega. And so we're going to identify that as the, and if you like, sine omega t. And we're just going to extract this once again as the amplitude. And we get now a similar equation. Actually, if you look back, it looks almost, it's exactly the same. It's just that in this case, we have a constant B field. And in this case, we have a variable B field. But we have a constant frequency. So, it's similar to the rotating coil. But B sub 0 varies, and F is fixed. Okay, so we'll get into the particulars of this in a minute. These are among the essential data you have to make sure that you record. So just make a note to yourself. And we have the area for both coils. It's here. Well, we'll hold off on this for a minute. And we'll get into procedure. Okay, so now we have the two, and okay, yeah, how are we going to analyze this data? This is a little more complicated, and there's whole separate videos for it. There's separate videos for all three, but I just want to get into what we have, just the background, and then what we're going to be doing. Okay, So you're gonna come in and you're gonna see this monster. It's been hiding under the table in the back. You may not have noticed. And you'll see that there's these two big coils and there's this Mongo steel through it. And on top, you'll see these two big blocks that can be actually moved. And the closer together they are, the more constant is the field in this area. Because you'll get some fringe fields here. And we also have a coil, and the coil is actually is smaller relative. So the coil diameter is much less than, say, this height. So we want to have a nice even field in there. So you'll see this there in this picture, this photograph, there's this heavy wire goes, and that is, excuse me, going to go to this system here. So you're going to have some kind of speed control, and that's that heavy black wire. And you're going to see the coil inside of here. It's encased in some plexiglass, and it's quite small. And we're going to need to not simply get the radius here, but turns out there's two radii, R and S. We'll get into that. And then you're also going to see a power supply, a variable resistor, and an ammeter. So what happens is that we have, once again here for this, we have a K value, remember that, for this magnet. So we can calculate the B if we know the current. So we have big Mongo electromagnet, very uniform magnetic field. We have a current flowing through it, and we know the current, and we can derive a K, which is beyond the class, but we just supply that to you. Right? So essential data are these two numbers, the K and the I, in say the big coils, if you will. Excuse me. Now, also, you're going to notice that there's a system of brushes, and a brush is just, well, you have these slip rings, and you have something that's held against it with a spring. We call it a brush. In our case, there's a disc, and on the disc are two copper rings, and you'll be able to see them. The disc, and that disc is here. And the disc rotates with the coil. And you're going to also see then, you see this disc, and then you're going to see this other plate, a fixed plate. And you're going to see these two metal buttons. and the two metal buttons are pushed against the disc, and you're going to see that they are, one is on the outer side, because one of them, and they both these spring buttons contact the copper rings on the disc. And so these are the brushes. The copper rings on the disc are the slip rings, and the spring-loaded buttons are the brushes. And you'll see on here, I don't think you can see it on, there's banana, here they are down here. So there's banana jacks, and you just plug in your patch cords. And all my handwriting, you can delete it, so you can use these illustrations if you want to print them. I mean, you could also just draw your own. I don't know. It's up to you. And you'll just connect it. In this case, we don't have a trigger signal. I don't remember off the top of my head. There might be, and then maybe we'll use channel 1 and channel 2. Okay, so what we're going to do is, in this case, oh yeah, remember we had said the equation we derived. Yeah, is this it here? Yeah. Let's bring this forward. Control C. Control, make it a picture so it's easier to manipulate. So you're going to make a table. And, right. We're going to make a table, and we're going to, let's see, the x variable is the frequency, and this frequency, so the speed control sets the frequency. Well, it sets, they usually, what do they call it in revolutions per minute? Yeah, which is frequency. Okay. But we don't read anything off of that. So, and then a corresponding EMF. So, what you could do for now, in the beginning, is simply to make a table of period, because you can measure that. And remember, this is your EMF 0. Now, remember this is also y equals mx plus b. So there's two fit parameters. So we need 8 data points. Okay. So then a little digression on the diameter of the search coils. So when you wind copper together, like in the magnetic field lab, we just assumed that, and I believe even there was maybe a couple layers of copper on those rings, but we just assumed everything was at the same radius. And we want to refine our measurement. So we realized that these coils, the copper has a certain amount of thickness that you can't ignore. Now, you might say that the radius is just the midway point between these two. But remember, we're talking about area. and the radius squared is involved. So it's not exactly the midpoint. There's an appendix to the lab with this whole derivation, but I'm not going to hold you responsible for that. Just pay some lip service. You have this picture, you write this equation out, and so this compensates. So that gets us the accurate radius of the coil. And remember then, so we have to record those things. We need remember the K and the I of the big coil. And we need R and S of the search coil. And that is written on it. You'll see it. It's there's a plate on top here, and I don't know if they show it in this lab manual. I haven't had a chance to rewrite as much as I'd like. In fact, yeah, see this picture here? There, right here. That's where your R and S are. And see this, the little coil right there. I need better pictures, obviously. Okay, so that's part A. And then the procedure for part B. So this is what you're going to wire up. There's this 1 ohm. Let me pause this for a sec. Okay, so there's this 1 ohm resistor, and it looks. Yeah, here we go. And it's got these ridges on it. So, to me, and it's about as big as your hand. It's pretty big, actually. Well, it's not huge, but let's say this is like 5 centimeters, and this is 5 centimeters, and then maybe it's 10 centimeters. So it's reasonable size. I don't know. I used to have one here, and I always say it looks like the shield generator on the ice planet Hoth from The Empire Strikes Back. This is the view from the Imperial Walker, if you remember. Okay, so we have so let's get the picture up here. I goofed there. Let's see, I thought we had a picture. And come on. Ah, there it is. Shitty picture. You're better off taking a photo. So these are the coils that are going to be generating the field. We're going to do 1 and 2. And then there's a tiny little coil there. And it's on this track. They're very old. They were made probably they were here when I was a student here. They're very old. We used to have a really great tech shop, and they made all this equipment, and some of it's still going strong. And so we're going to slide that. Let's see. Let's get the original picture. Where'd they go? Oh, of course, this is the very last. Oh boy. Okay. So that's the main coil here. And then the search coil here. That's a schematic representation. They're not going to be next to each other like that. I guess what we could do is, for real, get this. Just so if, I mean, I think it's crappy. I'm sorry I don't have a picture. I might have one. I'm just not organized enough to find it. Okay. And you'll see that there's banana jacks here. There's a banana plug, a nice two-pronged one. And, right. Let's pause for a sec again. Okay, so we plug in the surge coil to channel 1. We plug in the, we're going to put patch cords again to the this fixed resistor. Notice it's 1 ohm. And we connect that to channel 2, and we're going to trigger on channel 2. So this is one of those great times where we have a stimulus and response, because you're going to notice as you take these measurements that the search coil is going to get pretty fuzzy because the signal's going to get weak. Now, it turns out now we're going to hold the voltage, the V peak to peak of the transformer. See, it's not well, it's sort of adjustable, but we're going to keep it constant. So, our I peak to peak is just going to be equal to V peak to peak divided by R, but since R equals 1, it's pretty simple, right? You should check this one. I'll go over that in class. Okay, so we hold that constant, and we don't even need to look at channel 2 anymore other than to check it once in a while. And you're going to you're going to make a table of the Z position, and so this is the independent variable, and the dependent variable is the amplitude. So that's 1/2 V peak to peak, and that comes from channel 1. And in this case, I don't remember anymore how many data points, because the analysis is involved. Okay, so that's what you need. This is good enough to get us ready for lab in the coming week. So I'm going to stop this. It's already pretty long.